Good morning or good day, everybody. My name is Cindy, and I'm going to spend an hour with you going over some problems and having some fun with math. Right now in San Francisco, California, and we're connecting over 8,000 miles, which is unbelievable. Just one thing that I want to make sure we are all on board with. We're going to pretend that we are taking our brains to the playground, and we're not competing to see who is first or who is right. We are just gonna have fun trying something new. And you should also know that just by trying to solve a puzzle, our brains grow. And when we make a mistake, our brains grow even more. So please do not be afraid to make a mistake. Just start with the problem, see what ideas come to mind. You can discuss with your friends, and I will give you a few minutes for every problem, and you can work on them as you like, together with your friends or on your own. So I'm going to put this down here and move on to our first problem. Okay. Our first problem states, can you guess which figure is the odd one out? And I'm going to give you a few minutes to think this over. Don't rush to conclusions. And I think that what we want to do here in order to save time, Amit, is to just cut and paste to the solution. So now I'm going to, okay, so hopefully your teacher paused the video for a few minutes and you're all raising your hands to tell us which one you think is the odd one out. And one reason why I like to start with this problem is because we tend to rush when we get an idea and we think it's the right idea. We don't make sure to go back and check that it's consistent. So a lot of time when I put this problem in front of students, I have someone rushing over and saying, oh, I think this one must be the odd one out. So I usually have someone jump right over and say the yellow one is the odd one out because it's yellow and all the other ones are red. And then someone will jump and say, well, wait a second. There is also this one. It doesn't have an outline. All the others have a black outline. And then someone will jump and say, wait a second. This one here is small compared to the others. The others are roughly the same size. So if you had gone slower, already you would have noticed that there are others that look like they don't belong. And then finally, obviously, someone will jump and say, the hexagon doesn't belong because all the others are circles. And look what happens. There is one which nobody ever picks. And that one is the real odd one out because it doesn't have any characteristic that is different from the others. All right. We're going to move on to the next problem. And just a quick note to teachers, ask your students about their answer. And if there's more than one answer, perhaps let the students discuss why and convince each other about the correct answer. Most times they will find their mistakes on their own, and that is a really valuable experience. So let's try this new problem. This is a logic and spatial reasoning problem. And it says, out of these series of figures, there is one missing, and you have 8 choices underneath for the one that is missing. And can you figure out what is happening with number 1, 2, 3, 4, 5, 6, 7, 8? and which one should be the 9th figure. And teachers, you can pause the video here, let your students have a chance to think about it. And students, when you have an idea, you can raise your hand and let your teacher know that you are ready to share. So pause the video for 1 second or for a few minutes, whatever the students need, and then I'm going to reveal the answer when we come back. Okay, so we're back now. And the correct answer, let's do it together. What is happening here? We can see that the squares are jumping one ahead. So this one moved 1 square over, and this one also moved 1 square over. And now this one moved 1 square over, and this one moved to the line below. And in the next one, they all move 1 again. And again, this happens. And again, they all move 1 square over and another square over. What would happen here at the end? Well, this one would move to the corner. And that leaves us with either this, or this, or this, right? Those are the only 3 choices where we have 1 in the corner. But what would happen to this one? What do you think happens to this one? Well, this one now will move to the beginning. So number 5 is the correct answer. So the squares are just traveling 1 over to the right, and when there's no more room in a line, they go down to the next line and down to the next line, and when the 3rd line is used up, then they move to the 1st line again in a circle. Fantastic. I hope you all got this one. Okay, let's try a new problem. Can you make this equal to 101? And you can use any operation: addition, multiplication, division, subtraction. Can you place the operations in the little boxes and make those 4 tens equal to 101? And here, teachers, again, pause, give your students a chance. And students, remember, you can discuss with your friends. And let's see if you can come up with more than one way to do this. If you found one way, try another way. And let your teacher know when you're ready to share. Okay, so we're back. You've had a chance and you've all shared, and I'm going to reveal one way to do it. So if I multiply 10 by 10, I get 100. And how do I make one more? Well, I'm going to add 10 divided by 10, which is a 1. So here I have 100, and here I have a 1. And when I add them together, I get 101. Is there another way to do this? Well, you can invert it. You can do 10 divided by 10 and then add the 100, which comes from the 10 times 10. Did you find another way? Perhaps there is another way. I will let you discover that, or discover that there is no other way. Either way, you're using your brains and growing new connections in your brain. All right, let's move to the next problem. So this problem is very interesting. It helps us get better at working systematically. You have this grid, and inside there is 1 square that is painted blue. And the question is, how many squares in this grid contain the blue square? So for example, just to clarify, if I take this square this big square contains the blue square. So that's 1. And this square, a 3 by 3 square, also contains the blue. So that's another 1. And the question is, in total, how many squares in this figure contain the blue square? So pause the video for a few minutes, work systematically, and let's see if you can find out the answer. Okay, so we're back, and I've worked it out myself, and this is what I came up with. So the answer is 19. There are 19 squares that contain the blue little square. And the way I've counted this is I've started with counting how many of the 5 by 5 squares, which is there is only 1, which is this big one. So we have 1 5 by 5. How many 4 by 4 squares do we have? We have 1, the next one over, 2, and then we go down 1 line, 3, and 4. So we have 4 4 by 4s. Now how many 3 by 3s do we have? 1. I'm going to change color, make this easier to see. We have 1, 2, and 3 up here. And then if we move 1 down, we have 3 more, that would be 6. And we move 1 down again, we are at the bottom, and we have 3 more, so we have 9 3 by 3s. And if we go 2 by 2s, well, this one doesn't contain the blue square. The only ones that contain the blue square are this one, 1, 2, 3, and 4. So we have 4 2 by 2s. And then we have 1 by 1, which contains the blue square, which is the blue square. So if we add all these up, we have 5 plus 5 is 10 plus 9, 19. And there you go. So if you work systematically, you arrived at the correct answer. All right. One more problem. Here we have 3 figures. Figure 1, figure 2, and figure 3. And there is a pattern of growth. Can you see how these figures are growing? And if you figure out how they are growing, perhaps you can tell how many squares will be in figure 10. So when you continue like this, figure 4, figure 5, figure 6, and so on, how many squares in total would be in figure 10? And if you figure that out, you figure out the rule, then perhaps you can also tell how many squares will be in figure 100. So teachers, let's pause the video here and give the students a few minutes to try and figure out how this series is working and what is that secret pattern that is making these figures grow. Okay, so we're back. And there are many ways to see how this is growing. So I will share the way I see it, and hopefully it's different from the way some of you saw it. And so you get to see how different people think in different ways, and it's all fantastic. We are all different, but we all have a very powerful brain in our heads that we can make more and more powerful by training in solving these problems. So the way I saw this is like this. I saw 3 squares that are fixed, that are the 3 squares that we start with. So those 3 squares, in my mind, were the beginning. So at the beginning, I have 3 squares in, let's say, figure 0. So this would be figure 0 for me, just 3 squares. And then in figure 1, we have added 1, 2, 3, and 4 squares. So figure 1, we've added 4 squares. Figure 2, we have the original 1, 2, 3, and 4, and now we've added 5, 6, 7, and 8. So now we go from 4 to 8. So we go from figure 1, which is 1 times 4 equals 4, to figure 2, which goes 2 times 4 to give us 8. So you can see now that in this figure we have the original 3 plus 4, 7 squares, and in this one we have the original 3 plus 8, which gives us 11, and then, you guessed it, in this one we have the original 3 plus 12, which is 4 times 3, because it's figure 3, and that gives us 15. And now that we've cracked this rule, and let me write it here, so we have 3, because it's figure 3, times 4 gives us a 12, and 12 plus the original 3 gives us 15. So now if you go to figure 10, you would have the original 3 plus figure 10, which means 10 times 4. And that would be 43. And for the 100, it would be the original 3 plus 400. 100 times 4. And that is 403. And if you've gone even farther, then now you have a power in your hands. You can tell me any number of squares for any figure. So if I say how many squares there are in figure 1436, you can tell me. You can use this formula and you can tell me. All right. Next problem. Okay. So this will exercise a little bit your multiplication skills. We have the numbers that are beside each row and column. So these numbers and these numbers. Oops. Sorry. My pen is misbehaving, but you get it. All right, so the numbers beside each row and column indicate the product of the 3 numbers in those 3 sets. So that means that this number multiplied by this number multiplied by this number equals 28. And this one multiplied by this one and by this one equal 180, and so on. like that for every column and for every row. Then the other piece of information that we get in this problem is that the numbers 1 through 9 are used and are used exactly once. The numbers cannot be repeated. So the question here is, let me erase this so it's not confusing. The question here is, how would you place the numbers and what number would be in the middle where the red question mark is when you finish placing all numbers 1 through 9 without repeating, so that when you multiply the numbers in the rows and the columns, you get the numbers that are on the edge. And here we're going to pause so that you can work it out. Okay, so hopefully you're all very eager to share with your teacher. And I'm going to move the next slide so that we can solve it together. So here are the digits that we must use. 1, 2, 3, 4, 5, 6, 7, 8, and 9, and we must use only once each of them. So the first thing that I notice is that 28, which is 7 times 4, and 42, which is 7 times 6, they both share the multiple 7. So I'm going to guess that I should place the 7 here. And now I have used up the number 7. The next thing I notice is that the only way that I can get 28 with 2 more multiples is either a 4 and a 1 or a 2 and a 2. So I can do 2 times 2, 4 times 7 is 28, or I can do 4 times 1 is 4 times 7 is 28. But I cannot do a 2 and a 2 because I will be using the number 2 twice, and that's against the rules in this problem. So I know that these two numbers are a 1 and a 4. So I'm going to be using the 1 and the 4 and the 1. And in which order, I don't know yet, but I can notice here that 180 is much bigger than 48. So I'm going to guess that I should put the smaller number here, which is going to be shared with this row to make the 48. And I'm going to place the 4 here. Okay. So let's see what's happening here. I need to make a 6 out of these 2 boxes to make the 7 and these 2 numbers come up to 42. And one way to do that would be to do a 6 and a 1, but I cannot do it because I already used the 1. So the only choice is to do a 3 and a 2. So I would be using the 2 and the 3. And in which way to do it? Well, I don't know, but I'm going to use the same logic as before. And I'm going to do the bigger number here and the smaller number here because these two are proportionally bigger and smaller. So now we've cracked these 2 rows. We don't know we're absolutely correct, but we know that we used the right number. So now we have a 5, a 6, an 8, and a 9. So let's see. If I break the 120 into 3, I have a 40. To get to 40, I can do with these numbers, I know I can take a 5 and an 8. Either a 5 and an 8 or an 8 and a 5. I don't know which one to put here, but this combination would work. And then I get the 6 and the 9 remaining. So if I break 180 into 4, that gives me 45, correct? If I divide it into 2, it's 9, and if I divide it into 2 again, that's 45. So I would need a 5 and a 9 to make 45. I cannot make 45 with an 8. So I'm going to discard the 8. I'm going to retain the 5, which gives me a 20. 4 times 5 is 20. And then I know I have to put the 9 here to get to 180. Right? So now I've used the 9 and I've used the 5. And I know this is the 8 here. And then the only other number missing is the 6. And 6 times 8 is 48. Times 1 is 48. And we are done. So the correct answer, or the answer to the problem, as stated at the beginning, is 8. All right. It takes a little bit of perseverance and trying out different things sometimes, erasing a little bit and starting over. If you persevered and you got to it, then you've developed a very useful skill, which is sticking with a problem. I'll tell you an anecdote. Albert Einstein, you might have heard that name, very famous scientist, Nobel Prize winner for physics. He said he's not more intelligent than other people. He just sticks with problems longer. So this problem we just cracked is a perfect problem to practice sticking with a problem for a long time. All right, moving on to the next one. This is our final problem of the day. And this is called a can-can puzzle. It was invented by a math teacher in Japan, and he wanted to give his students a chance to practice arithmetic, but in a fun way. So let me quickly go over the rules, and then we'll solve this one together, and then I will place a new one for you to do on your own. So your goal is to fill in the whole grid with numbers, making sure that no number is repeated in any row or column. Then, because this is a 3x3 puzzle, you can see that there's 1, 2, and 3, and 1, 2, and 3. Because it's a 3x3 puzzle, we're going to use the numbers 1, 2, and 3 only, and only ones in each row and column. Now, notice that there's these heavily outlined areas. They're called cages. And those cages contain numbers that need to satisfy a criteria. The top left corner here of each cage has a target number. In this case, for this cage is the number 2. And it has an operation. In this case, the negative sign for subtraction. So when you enter numbers in this cage, you need 2 numbers in this cage. They must satisfy that their difference is equal to 2. And then finally, I skipped over this rule. You notice this cage is just 1 square, and that is a freebie. It means that we can just write down the number that is given to us. So that's a freebie. We already know that's a 2. And that means that this cannot be a 2, and this cannot be a 2. The next thing that I notice here, and now we need to use logic to figure out how to place the other numbers. So I notice in this cage, I must place 2 numbers that add up to the number 3. And the only 2 numbers I can use are 1 and 2. But in which order? Should the 1 be here and the 2 here? Or the other way around? And the answer, you might have guessed already. The answer is that the 2 must go here, because if I put it here, then I would be using a 2 twice on that column. And that is not allowed. So now I know that the 2 and the 1 go like this. And now, obviously, the 3 must go here, because we must use the numbers 1, 2, and 3 in each row and in each column. And that helps us solve this square up here. Now we know this must be a number 3. 1, 2, 3. So what other number should I put here that subtracted from or from 3 will give us the number 1. And the answer to that is that a 2 goes here. 3 minus 2 equals 1. And what number should I put here so that these two numbers divide to give us a 3 as an answer? And the answer is 1. And notice we haven't repeated any numbers. So now we just complete. We're missing a 3 here. And then we're missing a 1 here. And notice that 3 minus 1 equals 2, which is what we were supposed to get. So now this can is solved. Okay, so the next one I'm going to put up on the screen is a 4 by 4, which means we can use the numbers 1, 2, 3, and 4 in each row and in each column without repeating. So here you go, and I'm gonna just let you pause this for a few minutes so that the students have a chance to go over this. Remember, if you have a single cage like this one, you can already fill it in. So this would be a 3, and this would be a 3. The rest, I'll let you work it out on your own. Okay, so hopefully everyone's filled out their can puzzle and everything is consistent. You can always tell if you're right because you can check that you haven't repeated any numbers in every row and column. And that every row and every column has all numbers, 1, 2, 3, and 4 in some order. So the next slide will show you the answer, and I'll leave that up so that you can check your work. Here you go. Okay, so quick note here for teachers. Put it on my screen as well. There is a website called cancanpuzzle.com, and you can go there and download or copy can puzzles of various difficulties, from a 3 by 3 with addition only, like similar to what we just did, which what we just did was a little bit more complicated because it had addition, subtraction, division, multiplication, but you can just give your students a 3 by 3 with just addition, or you can keep challenging them and making these can puzzles more and more sophisticated, where you have all operations in a big grid. And this is a great little puzzle to bring to class once in a while to practice arithmetic and just have a little friendly competition to see who finishes first. But speed is not important, actually. It's just a little practice for our brains. All right, so thank you for playing. And teachers, thank you very much for exposing your students to this activity. I like to say that when we play, we make gray. And when I say gray, I am speaking about the gray matter in our brain. So by doing these problems in a very friendly, stress-free way, without competition or without hurrying too much, we have a chance to develop our brain. And mistakes are great if you find them, because when you find the mistakes on your own or with your friends, you make amazingly deep connections in your brain. So never fear, just always try. Thank you so much, and keep playing.